We're about to dive into an experiment that seems incredibly simple on the surface, but its results are so bizarre, they completely upend our sense of how reality is supposed to work. You're going to see how a single particle can act like it's in many places at once, and how just the act of looking at something can change what it does. This is the incredible story of electron interference.
All right, so let's jump right in with a simple thought experiment. Imagine you've got a gun that can fire single electrons, one at a time. In front of it, there's a barrier with two tiny slits in it, and behind that, a detector screen. Now, if you shoot these tiny particles one by one, what do you think you'd see on the screen? Common sense says you'd get two lines of hits, right? One behind each slit.
And to start with, everything looks perfectly normal. The first few electrons fly out, and each one makes a single, tiny dot on the detector screen. Exactly what you'd expect from a little particle, kind of like a tiny grain of sand hitting a wall. So far, so good. Nothing weird here.
But as we let this run, firing thousands upon thousands of electrons, one after the other, something else starts to happen. Something that makes no sense at all. Take a look. Those dots aren't landing randomly. They're starting to form clumps in very specific places, while avoiding other places completely. A pattern is definitely emerging from the chaos.
And then, you see it. The final result. This is the moment that breaks classical physics. We don't get two simple bands. We get this. A whole series of bright and dark stripes. This is an interference pattern. It's the kind of pattern you get when waves, like ripples in a pond, pass through both slits at once and interact with each other. But we were sending particles one by one.
So let's just pause on that for a second. We sent individual particles. Each electron went through the experiment all by itself with nothing else around to bump into. And yet, somehow, they arranged themselves into a pattern that could only be created by waves interfering. So what was going on? Did each electron somehow interfere with itself?
To even begin to wrap our heads around this, we've got to go back in time, to the 1920s. The answer starts with a radical idea from a physicist named Louis de Broglie, an idea that gave every piece of matter a second, hidden face.
And what's really amazing here is that the theory explaining this phenomenon actually came before anyone had done the experiment to confirm it. It all came from this young French physicist, Louis de Broglie, as part of his PhD thesis, of all things, back in 1924. He proposed something that would totally change physics.
His big idea was this. What if this whole wave-particle thing wasn't just for light? He put forward the hypothesis that all matter, and I mean everything, electrons, atoms, baseballs, even you, has a wave associated with it. He called them matter waves.
And he managed to capture this whole mind-bending idea in one beautifully simple equation. On the left side, you have lambda, the wavelength. That's pure wave stuff. And on the right, you have p for momentum, a classic property of a particle. This little equation right here is the bridge connecting the two separate worlds of particles and waves.
Okay, that is a pretty wild theory. But a theory is just an idea until you can prove it, right? Science needs evidence. So how did anyone manage to prove that these ghostly matter waves were actually real?
Well, you know what? The proof showed up astonishingly fast. We're talking just 3 years after de Broglie's thesis. In 1927, two totally independent experiments, one by Davison and Germer in the US and another by G.P. Thomson in Scotland, both confirmed it. Electrons really do act like waves.
The Davison-Germer discovery was actually one of those classic happy accidents in science. They were just studying how electrons bounced off a piece of nickel. But then, a little mishap in their vacuum chamber accidentally superheated the nickel, and by pure luck, it caused all the nickel atoms to line up into a perfect orderly crystal grid.
And when they started shooting electrons at this new, perfect crystal, everything changed. Instead of scattering randomly, the electrons came off in these distinct, sharp peaks at very specific angles. That was it. That was the smoking gun. The perfectly spaced atoms in the crystal were acting like a diffraction grating for the electron waves. De Broglie was right.
So, okay, electrons are waves. But wait a second, that just makes our original problem even stranger. If it's a spread-out wave, how does it hit the detector screen as a single tiny dot? And how does it know where to land to help build that wave pattern? Well, this takes us to the absolute weirdest part of quantum mechanics, the price of knowing.
Get ready for this, because it all comes down to one simple thing, whether or not we're looking. Here's the deal. If you just let the electron do its thing and you don't check which slit it goes through, it behaves like a wave, and you get that beautiful interference pattern. But, and this is the kicker, the moment you put a detector by the slits to see which path it took, poof, the pattern vanishes. Gone. You just get two boring clumps.
It's as if the very act of knowing which path the electron took forces it to stop being a wave of possibilities and just pick one. It's forced to act like a particle. It's like the universe has a fundamental rule. You can see the wave, or you can see the particle, but you can't see both at the same time. The more you know about its path, the less you see of its wave.
Now, I know this all sounds like some kind of philosophical mind-bender, but this strange duality isn't just a curiosity for physicists to puzzle over. It's a fundamental principle of nature that we've actually harnessed to build some of our most powerful technologies.
You're probably wondering, if everything is a wave, why don't I see a baseball spread out and diffract when I throw it? Well, it all goes back to de Broglie's equation. For a big, heavy object like a baseball, the wavelength is so ridiculously, unimaginably tiny that you could never hope to measure it. But for a tiny electron, its wavelength is on the scale of nanometers, about the same as the space between atoms in a crystal. That makes its wave nature not just detectable, but incredibly useful.
And here's how we use it. Because an electron's wavelength is so much shorter than the wavelength of visible light, we can use them to see things in far greater detail. That's the whole magic behind the electron microscope. We're not just looking with electrons, we are literally using their matter waves to create images of a world totally invisible to normal microscopes, letting us see things like the actual bacteria that cause tuberculosis. So this core principle, that particles can behave like waves, is so much more than an abstract idea. It's the absolute foundation for technologies that let us explore the microscopic world in ways we could have only dreamed of a century ago. Which leaves us with one last, profound thought to chew on. We've seen that an electron seems to exist as just a haze of possibilities, a wave, until we measure it, forcing it to pick a spot and become a particle. So, if the world only becomes definite when we look at it, what does that say about the nature of reality when we're not looking? It's a question that keeps physicists up at night.